an introductory welcome kind of lecture. We'll go through some examples of machine learning, definition of machine learning, and like a brief overview of what machine learning is about. And I'm going to introduce the structure of the course, how we are going to assess the course, and what topics in general we are interested and we are going to cover, okay? I really hope that you take the best out of this course because it is kind of an important core course in computer science. It's really important and fundamental, foundational for many other courses, okay? Such as deep learning. Deep learning is everywhere. So if you look at relationship between machine learning and deep learning and AI, so we have like a larger circle of AI, which is artificial intelligence. Inside that AI, we have machine learning, and inside that machine learning, we have deep learning. However, deep learning is such a successful trend that you can find it pretty much everywhere. It doesn't mean that we have to forget about the mother machine learning, okay? So we have to make sure that we are getting the foundation of the deep learning right, and the foundation is basically outlined in machine learning, okay? So let me introduce the lectures of this course. In the left, you see Dr. Fanny Deligiani. She is a senior lecturer in our school, and she has the expertise in machine learning in healthcare. And my name is, as you could see, and maybe may recognize me. And this picture goes back to maybe 4 years ago, 3 years ago. Have I changed a lot? Look at, okay, all right. So, yeah, so I am also a senior lecturer in the same school, and my expertise in medical image analysis. So I take approaches from deep learning, machine learning, and particularly statistical machine learning and deep learning, and apply it to a problem of medical image analysis. Like, try to extract information from medical images like MRI, CT, X-ray, histopathological images, try to quantify some data out of those images and deliver that data to physicians, doctors. Okay, so that's my overarching thing. So we are going to give the main lectures. In addition to us, there will be some guest lecturers. One is already confirmed, Dr. K. Yuan. And these guest lecturers, they are going to talk you through your courseworks. Okay, so and don't worry about courseworks and how it's related to your exam at the moment. But these are like a practical project-like works that you undertake to gain some credit towards your final mark, okay? So I'm trying to secure one more guest lecture, but it's so hard because everybody, you would admit that everybody is nowadays busy, especially in a busy school such as a School of Computing Science. It's a bit difficult, okay? Let's see. All right, so the first question that comes into my mind, and maybe your mind, is why we should bother about machine learning? Of course, this is kind of a teaser, okay? So machine learning is very beneficial at the moment. This new era, Andrew Ng, who is a professor in University of Stanford and might be known to many of you, he's a real figure in machine learning. He says he believes that machine learning is a new electricity. So when electricity was discovered by Edison, it propagated through a lot of things and revolutionized our life, right? So his perception and many others' perception is that the machine learning is going to revolutionize and change our lives with the same speed, It's like electricity, right? It's fast. So you can find it in healthcare, environmental science, battling challenges of human being. But apart from ethical and moral objectives that you might have in your mind, it's a rewarding job. So you could see that how the trend of salary is changing over the years, in 2005 up until now in the UK. So a person with about 80,000 British pounds a year is just about the average. It's not a luxury salary. So you take it from there. So if you become an expert, it's almost guaranteed that you're going to have a comfortable life. Okay? Okay, and that's the reward for whoever wants to excel machine learning. So let me start by trying to intrigue you, giving some examples. So examples of machine learning, applied machine learning. So where we see machine learning. So first one maybe in spam filtering, right? In my university email account, I could easily see that I get a lot of spam emails automatically differentiated from important emails and all dumped in the spam folder. It's not like someone is sitting there trying to isolate them from important emails. There is certainly an algorithm behind the scene that works. And so most likely it's a machine learning algorithm that looks at the text, what's happening inside the text. So it's like a language model that differentiates the spam emails and dumps them away. Okay, so that's one example. Face detection. Face detection, wherever you have security concerns or there is a security concern, face detection is a good way of authenticating people who are allowed, for example, to enter somewhere, a really important, secure place. Pedestrian detection, advanced cars. Some cars have cameras and can detect pedestrians. So for better security, they almost know what's happening around themselves, the cars, okay? So they recognize that someone is approaching, and if you are lazy, or I am lazy, I am sleepy, so I don't press the brake, the car is going to automatically stop. And that's thanks to pedestrian detection. This is kind of an image analysis, image processing task. Movie recommendation. If you have Netflix at home or Amazon Prime, you know what I'm talking about, right? So you have a history of watched movies, and based on your history, Amazon says, hey, please watch this another movie. I think you're going to like it. So it's like a recommender system. And voice recognition. Busy centers. You call busy center with a wish, a hope that someone will pick up and answer you, but a machine comes up instead, right? And you engage with machine, and 1,000 times asks you address, your name, etc., etc. Maybe it's not the best way. Maybe it's not like the most mature form of machine learning or deep learning yet, but we'll get there. Okay. Any interesting examples that you want to mention, any of you? It's a burning example that you want to say. No? Yes, please.
We have object recognition, we have predictions as well.
Object recognition, prediction, yes. So making sense of different objects, what's happening around robots, for example. Yeah, good. Okay, by the way, I don't want to have a dry lecture, okay? So I want you to get really engaged and feel that you are here for a purpose. So it's not like about, oh, it's a class, it's a lecture, you have to sit there, you know. It's like, no. So please enjoy and get engaged, okay? Okay. So, and the second thing that I want to mention is basically a definition. It's not critical to know what's the exact definition of machine learning, but it's kind of important as well, because it helps us to understand and differentiate whether something is machine learning or not. Okay? So Arthur Lee Samuel, which was an American scientist, in 1959 actually, founded machine learning, and he defined machine learning as the field of study that gives computer the ability to learn without being explicitly programmed. Okay, there are two key words here that I wanted to emphasize, and the first one is learn. The learn is to learn from where? Is learn from the data. So there must be some data. So we have provided some data to the computer, and the computer wants to learn some patterns. For example, to identify similar objects, to predict something, to conclude, and to make sense of the data. Okay, and we'll see what I mean exactly in next slides. But the other key word that I wanted to mention and emphasize, the explicitly programmed. If it is about making prediction, let me give you an example and confuse you a little bit. If we have some radiators here, we must have somewhere, right? And we turn them, increase the temperature, right? And if I ask, what will be the temperature in that corner of the room after 20 minutes and that corner of the room after, let's say, 10 minutes? So how do you go about that, solving this project? So if we want to really tackle this, we have to solve the partial differential equation that governs how heat is transformed in a room or a compartment like this, okay? So we have differential equations, and then we have to maybe discretize the differential equation. It is a physics-based computation. So we exactly know what's happening, and we compute that. There's no example given of a similar situation. We're exactly trying to go through the principle and predict the temperature after 20 minutes there, after 10 minutes there, okay? And that's a physics problem, okay? That's not machine learning, because the computer, in this case, is explicitly programmed to solve the differential equation of heat. Another example is like in our spam detection, if someone goes around and says, hey, computer, if you find 3 letters, or letters such as award, account number, money, and you have won, something like this, then most likely it is a spam email, so get rid of it. But this way of programming a computer is an explicit programming. Machine learning is different. Machine learning actually allows us not to deal with the underlying phenomena for the problem. It's like a superficial solving the problem. Like without understanding what's happening between the variables, you want to make sense of them. And that's the beauty of the machine learning, because it simplifies the problem. How? By seeing examples. My own definition of machine learning is that learn through the examples. Okay? So we are given examples, actually the algorithm, that the computer learns by looking at that examples. Okay. Yeah, as I said, machine learning starts with data. So we must have data or examples. And how data is derived? Well, initially we don't have data, right? So we have objects, and we have objects that, these objects could be people or other things in the world. So we want to derive some data from these objects, and therefore make our examples or our data to start with. So in case of, for example, people, I'm talking about their health records. For example, blood sample health records, or blood pressure measures, or images or temperatures, right? The health records of people, their tastes, other things from the world, like cars, like pedestrians. I'm talking about images of cars, of pedestrians, of people, again. Maybe animals or sounds, examples of sounds, like, right? So, so we derive these examples and quantify them. Basically, we quantify them to construct our data, okay? And then we go and we do the next phase of machine learning. Don't worry, I'm going to basically give you more examples and explain the stuff a little bit more clearly. So what types of machine learning we have? So dominant types of machine learning are the following: supervised, unsupervised, and reinforcement learning. Okay, what is supervised? So these are task-driven. So then the prime examples of these are classification and regression. Unsupervised is data-driven. I'm talking about clustering. It's like making things or patterns cluster, or similar things come together to make groups. And the reinforcement learning, these are goal-driven, and we're not going to cover this, but here we have an agent that interacts with the environment, and we have a time element that it interacts with the environment and it gets rewards back. For example, a standing robot. So if he properly stands, there will be some reward in the algorithm that tries to train the robot. Okay, so this is like more advanced, but the important part, the important types of machine learning here is supervised and unsupervised. I'm pretty sure you didn't get it. Okay, so let me cut the chase and give you some further insight. Okay, so let's see what's happening in supervised and unsupervised. Most of the cases, right? We have a table, guys. Okay, in fact, we have a table. So this is our table. Right, okay. Here we have X elements, here we have Y elements. We have X, these are the data. These are the things that we have extracted from the observations. We call them features, okay? So every object is therefore transformed to set of features, okay? And these are measured. For example, a height and weight of a person, or a sample of a flower, okay? So we can have multiple features. So here in this table, each row, right, each row will be a sample. So feature 1, feature 2, etc. And we can have feature n, okay? And here we have what is the corresponding output for that row, okay? So this is target value we want to predict, or the machine learning wants to predict, okay? So let's call this T, okay? So, and we can have multiples of these rows, like T1, T2, etc., etc. And we can have, like as I said, different number of the rows, okay? So if you are dealing with a table like this, where you both have access to features or the measurements from the data and the corresponding target value for each of the rows, then you have supervised or unsupervised. Tell me. Supervised learning. Supervised, because the task is supervised by the Y column, which is the target column. Okay, so this is called supervised. So The supervised learning itself, as you could see, we have put classification and regression, okay? So how these are different from each other? So if the target values or TN values are discrete kind of types, or the categories that you want to predict, for example, cats, dogs, healthy or patient or unhealthy categories, okay? These are discrete concepts. This is called a classification task. But sometimes these target values are not continuous. They are they are not discrete. They are naturally continuous, like predicting a temperature in our, like a heater example. The temperature can be any continuous number, in fact, right? In that case, we are dealing with a regression problem, but it's still a supervised problem, okay? Got it? Strangely, sometimes we don't have the supervision. I mean, the T column or the Y column is completely missed from the data. But we are asked to predict them. Can we? Yes. And you'll see that how is it possible very clearly through an example in this lecture. We predict or we infer the outcome or the target data, like the T values, from the data itself. And this is called unsupervised learning. It can be regression type, it can be classification. Classification is unsupervised classification. It's like we don't have it, but unsupervised classification is clustering. Kind of, you know. So clustering is to try to guess or predict the types and categories of like the objects. Okay, and reinforcement learning, leave it for later. We're not going to touch it in this class. So, how we are going to solve this problem? Do you have any idea? How can we map a bunch of features F1 to Fn, which are different measurements from an object, to its corresponding target value? Any idea? Yep. Yes, we can use graphs and we can have a look at the mean, okay? But in general, the thing that is going to map F's to T's is called a model, okay? So what I'm talking about is like we can write in general, T is equal to a model, let's say F, a model of F1 to Fn. It's a function that takes these features and maps it to the T, okay, target. And generally, this function has some parameters. So let's call them theta. So any function needs parameters. Like a linear function, it has the slope, and it has like the distance from the x-axis, the intersection of the y and like the line itself. So, so our task, therefore, in learning is to determine this theta, the best parameters that like the transfers that features will target in the best way possible, with least error. Okay? So this is like really the big picture, a little bit fuzzy picture, okay? But I just wanted to quickly pull you out from the cloud. Okay, so this is like a hook you can have for now. Okay, so let's proceed. Supervised learning, regression, I think you must feel now better. So as I said, regression is supervised, and it's about learning a continuous function from a set of examples. Here, what are our examples? So each of these black dots is an example. It's a data point. Each of these black dots that you could see is a data point. Someone has gone through and has done the hard work for us and collected the data. We've got maybe tens, maybe 100 of them here. And we have the target value here along the y-axis. So this is the target axis, y. And the feature axis, how many features have we got here? How many features do you have for each data point? Any idea? I'm hearing something. Only one. One, no, one. We have one. Why? Because look, every data point has its own feature here and its predicted value over here. So y here, f here. So this is a one-to-one mapping problem. It's not, we don't have two features. One of them is the target. It's not feature. The y is target. X is the feature. Okay. And so, but you might think, okay, but maybe I had this already. I had encountered this problem somewhere in the math. Yeah, you're right. And this is called a regression problem. And the same name applies in the math. So we are basically regressing these points. And as I said, model is something that actually maps the features to target value. So we have here different model or different regressed curves. The red bit that you could see are different models. Simple model, like the one that our friend said, it's like just about the average of the points. Does it perform well? No, not really. It's not following the trend of the data. Second model is a bit better, maybe a quadratic. Third model, it is a polynomial of degree of 3. And the fourth model, you could see here's situation has got a bit better because it's more flexible. And the fifth model is even the better, right? Okay, so how many parameters do we have in the first model? Any idea? Yes, absolutely, 2. So you can say, for the first model, y is equal to a1 f plus a0. Here, a1 and a0 are the parameters of that line. I'm talking about this line, this guy. It's a line, right? A line of f. What about the second model? How many parameters have we got there? Go on. Don't worry. Say something. Yes, absolutely. So we have a2 f powered 2 plus a1 powered 1 plus a0. How many parameters therefore? 3. a2, a1, a0. So for the third model, how many parameters? You can by now guess. 4. And for a polynomial of degree of n, how many parameters do we have? N plus 1, right? And the degree of that polynomial is a free parameter that user must choose. Like, it's up to you to choose one. So, but, yeah. how we are going to, how are we going to calculate that? Do you know what that process is called? Training. Yeah, we are going to calculate those parameters, and the process itself is called training. So training is the way that we have to go through in order to determine the best parameters, okay? That's called training, okay? So, guys, but this slide is really beautiful. So as you could see, when I went from a degree of 1 to the degree of 5, the fitting got better, right? Better and better and better. What about just increasing the degree? Maybe a degree of 100. What's going to happen? So if you have got n data points here, n data points, for example, 100 data points here, I'm talking about the number of the black dots. And if you enjoy increasing the degree of the polynomial, making the model, wow, it gets better. Let's continue this. And have a polynomial of degree of 99. How many free parameters you have to solve or find? 100. How many data points you have? 100. You have 100 unknowns, 100 facts. You can exactly determine the free parameters in such a way that your curve goes through each of the data points exactly, in such a way that the fitting is perfect. Okay? Is that good? No. And what is called? Overfitting. Exactly. We want to avoid it. Why? Philosophically, why? Any idea? Yeah. Any other idea? Yeah. Kind of. Thank you. Let me cut the chase. Because we always have noise in the data, we always have the noise, right? If you're measuring the temperature, if you're measuring the stock, there might be fluctuations that are not actually due to trend of the data. It might be that I didn't have a good day that day, or the temperature the sensor was broken, basically the noise. That is irrelevant to data. And if you fit your data, if you fit a model to training data perfectly, you are going to fit the noise perfectly, therefore fail when it comes a new data, as our friend is saying there. And in that case, our model will fail badly. And in terms of the machine learning, they say that the model doesn't generalize well. Doesn't generalize, and that's called generalization. You want to have models that generalize, that learn robustly from the data and apply that to test data. Any other data that we haven't seen and is yet to come is called test data. Whatever we see here is called training data. Okay, so, and let me tell you a golden rule of machine learning. So if you have n data points, and if you have m parameters to fine-tune, to train, if m is larger than 1/10 of n, then there is a risk of overfitting. In other words, if you have 100 data points, the maximum degree of the polynomial that you could choose safely is around 9-ish. More than that, you risk overfitting. But there is another risk also, and it's called underfitting. Underfitting. Do you see the underfitting problem here? The first model is underfitting, doesn't fit the model. So what we should do with the models? What model is correct? We don't have a correct model. And the branch of machine learning that deals with the problem is called model selection, okay? But there is no, as I said, there is no right or wrong model. Some models are more useful than the other models because they provide better insight. And that is actually what Mr. George Box thought and believes. It says there is no true model. As long as they are like providing something, some insight, some knowledge, help us to understand what's happening, and we accept them as they are. Like, and his example comes from his physics. PV is equal to nRT. Have you heard of this rule or physics equation somewhere? It's like a neutral gas relationship, pressure, volume, and the rest of the things. Okay. The other form of supervised learning was classification. And classification, it's like geometrically is like, it's a bit different from regression. Did you see that all of the points here were black, right? Here, the data points, some are blue, some are red. They have a carry, they carry a third piece of information in them. And that's the color. The blue data points are a type of blue, and the reds are a type of red, okay? So we have two types of data points here. So tell me how many features we have here? Two, yes. Because if you look at each data point, the third dimension that we don't really see, like protruding from the plane, is the color, and that's a target, right? But the features are along the x and y axis. So please pay attention. Y axis doesn't always mean that it's a target, right? So y here is a visualization of the feature space. Y and x axis are the visualization of feature space. We have two-dimensional feature space. So in summary, we have a bunch of blue points, a bunch of red points. So we want to use this distribution of the data points and draw a line. Or determine the equation of that line more specifically. In this case, I'm talking about this guy, this one. This is the decision boundary. Our job is to determine the best decision boundary. If the classifier goes crazy and the training fails for some reason, we can have like absolutely rubbish decision boundaries, something like this. Doesn't make sense, right? So that means that the training has failed. But we can have really, really nice decision boundaries. And once we have got that decision boundary, for any test data point that doesn't carry a label with itself, so forget about this decision boundary. So here's come a data point. And I'm attaching no color to that. Let's say the data point sits here. So do you say it's a blue or red type? It's blue, right? Why? Because we are human beings, and this is kind of a very simple problem. We have visualized the data distribution. We can see that, right? But sometimes we can't see anything. Like if we had 10 features, Anything more than 3, and we are screwed up because we can't really see what's happening in this space of the features, right? 2 dimension is okay. 3 dimension, kind of okay. But the 4th dimension, I'm sorry guys, you can't really see what's happening. So in that case, how can we justify that, you know, if you're getting the right class? So, so generally speaking, the equation for this decision boundary is y is equal to 0. Anything that sits right on the decision boundary, it's predicted, middle predicted man, let's say. Y is 0, right? And y is greater than 0 here, y is smaller than 0 here. So we are going to design a function that just by looking at the sign of that function, we can decide the class. Right? We can do it. And in high dimensional spaces, we have to do it because we don't have visualization tool or etc. And like examples here, disease diagnosis, spam email detection, etc. You can name it. Depending on number of features that you want to have from the object, you can have the same problem with 2 features or more features in higher dimension. So what is the process in machine learning we have to take? This is the standard process that we usually follow. Data collection. So basically, we go around and collect a bunch of data. Like these are objects, patients, pictures, samples. Then we go and find the features. And so before the era of deep learning, people struggled to go through this step, feature selection. Someone would come, okay, I will say, for a blood pressure diagnosis, I think we have to look at the maximum pressure. And someone else would come and say, I disagree. I would look at the ratio between maximum and the average pressure. And the other, you know, arbitrarily set of features were made by different users with the hope of that, you know, they would increase the performance and accuracy of classification. Nowadays, it has changed. Nowadays, and the art of deep learning is that it says, guys, you don't need to have to do the hard work. I'm going to find the best features for you from the data itself. Okay? So, and that's how deep learning is different from machine learning. So, the third one is model choice. We already saw that, examples of polynomials. And the training. The training, as I said, is the way that we decide or optimize those parameters. And the evaluation. Evaluation is to see how model performs when it comes to unseen data, test data, not the data that has contributed to train it. Any question? No? All right, okay. Okay, and let's have an example here. Right, okay. So, for example, if you want to have a classifier that classifies 3 types of flowers. So, what do you do? The first step is the data collection. You go around and you collect a lot of images of flowers. Most of the cases, you don't do this. Why? Because the data set is already given to you, or the task is given to you, okay? And the data is given to you. So, and then the second step is the feature selection. Someone who's expert in identifying different types of flowers and says, okay, I think if you go around finding the dimension of the petal and the dimension of the sepal, then your classifier might have some success, because the way that I recognize these flowers from each other is that I look at, you know, how, you know, these 2 dimensions are different from each other, what is their ratio, etc., etc. Right? So these are important. Okay. So based on that insight and knowledge, you go and take measurements out of each image. And then you make four measures, right? So you have sepal length, sepal width, petal length, and petal width, okay? So as you could see, you have got a matrix of measurements here, four in each dimension. And what's the meaning of like the first, like this one, for example? This one says, first of all, you know the meaning of the color right now. So the color shows the type of the flower. So you're doing a classified, basically supervised classification. So as you could see here, in the plane of petal lengths versus sepal lengths, you have got three clear distributions, right? Red bunch is perfectly isolated from the other bunch. So therefore, these two features are kind of important, right? So because they successfully differentiate these three types of the flowers. But some are not that successful. For example, here, look at this, distribution plane here. Sepal width versus sepal length doesn't mean much. So they're not discriminative features or discriminant features, okay? So some features are good, some features are bad. So once you have collected your four features, then you go and you choose your model. It can be a neural network, it can be a support vector machine, or decision tree. And then you train. So based on the repository of the data you have collected, meaning the features and their corresponding target value, that table that I showed to you, you optimize the parameters, you tune the parameters. And at the end, you have to evaluate the performance of the model. Basically, if you have multiple classes, here in this case you have three classes here, you want to have confusion matrix or matrix. Confusion matrix, where you put like each type of classes versus row and column dimension. You want to have large diagonals and small anti-diagonals. Because you want to say that something that is actually a setosa must be classified as setosa, or the majority of the setosas must be classified as setosas. So you don't want to have a setosa from here classified as versicolor or virginica. So in this case, 14 has been or have been correctly classified, and two others have been incorrectly classified. But we have multiple classes, so you have multiple cross confusion, and that's why it's called a confusion matrix. So you want to have large diagonal, small anti-diagonal, okay? Any question, guys? No? Okay, so to make it a little bit more realistic and close to actually what's happening in the field, I have chosen a paper of a PhD student. Actually, she was a master's student. She worked on classification of breast lesions in ultrasonography. And she wanted to classify whether certain lesions in breast is type of a benign, meaning relatively threatless or not dangerous, or malignant, means that could be a killer, okay? So, and I remember that we had a radiologist, a lady radiologist, and she came to the university and she said, when I tried to report the outcome of the ultrasound image to the patient and to the doctors who is going to treat that patient, I generally look at how the boundary of the tumor in the image is. it contains important information. The fuzzier and the more busier the boundary of the lesion, the more likelihood of the tumor being malignant. Okay, so basically it means that benign tumors have like more pronounced boundary, but also their shape is not too complex. As you could perhaps compare these two to these two samples, you could see that benigns are relatively round, not too crazy in shape. Okay, so but we are, human beings are so amazing creatures. So just by looking at these two pictures, you've already got a good insight to say which one is malignant, which one is benign in the future, okay? But how are we going to apply machine learning to this problem? So hearing this, that the boundary is important, we focused on the boundary. And we tried to get rid of irrelevant information. And that's called kind of feature selection. Because in machine learning, you wanted to minimize redundant information, redundant features. Redundant features always increase the dimensionality, and we have tiers of dimensionality in machine learning. You wanted to do the job with least amount of the features, least amount of parameters, okay? So the way that we went around basically looking at the texture around the boundary was like this. So once the image is given, we would segment the tumor. Segment means that we're going to pick up or identify the tumor itself. But that's not the end of the task. The task is whether to say, is to say whether this is a benign or malignant. Then around the boundary, we would extract a boundary band with a certain thickness, let's say 20 pixels, right? And our goal is to unfold the boundary. I'm not really sure what's happening here. Yeah, okay. Unfold the boundary to a stripe, a nice rectangular-like stripe. So to get rid of the shape information, because we just wanted to focus on the texture, how busy this or how crazy is this texture, okay? So, and we have done this, like you see that if we pick up this band here, like and try to unfold it and pull it to make it straight. Why we're doing this? Because it would allow us to apply image processing tasks, image processing tools in the next step. So we can apply Fourier transforms, Fourier descriptors, Gabor features, and don't worry about these acronyms and jargons. The task of these descriptors is to quantify the amount of the frequencies that exist in these images. So the busier the texture, the higher some of these Fourier descriptors, okay? So, and it's easy to apply the Fourier to an image. And this is called an image because it's a rectangle. But, this guy here, by itself is not an image. It's really hard to focus on that area. So we somehow interpolated the image and we derived the bands for each image. And as you could already see, the benign tumor or lesion has certainly a white region top and a black region here, whereas the malignant, because the shape is such a crazy thing, it has a lot of textures and irregularity. And as I said, our descriptors could quantify that texture. The other thing was because we have killed the shape in the previous step, we wanted to basically to have a look at the shape features as well. So if this is the shape of the feature, or the contour of the feature, the contour of the tumor. So imagine that this is the contour of the tumor. So the way that we went around this is to extract the signature of the contour. So to extract the signature of the contour, you put the center, or you compute the center of the contour, and you try to intersect the contour at any given theta, which is the angle, and determine the distance from the contour to the center of the tumor, right? And if you then change the theta from 0 to 360 degrees, making a full circle, you're gonna at the same time measure the d for every angle, and therefore you convert this like weird contour to a function, and this is called the signature of the contour. And because this is like a conventional function, then you can have Fourier descriptors applied here as well. So you can, so the idea, the heuristic about this is like around this like signature is that, as I said, imagine that you know, we have a benign benign tumor. So if you derive the signature, so what would be the signature for this guy? Sorry? Yeah, exactly. So this one will be like very flat, minimum change. But for this one, as you see, it's crazy. It goes up and down. It would have a lot of fluctuations. And that changes up and down. We'd say that I have a lot of higher frequency amount in myself. And that will be quantified by Fourier descriptors. So, and this is the second step of our machine learning process. My aim is to teach you machine learning process for this example. So once we've got the features, both from the texture and the signature of the tumor, some of these are morphological, some of them are textual, etc. Then we can have the model. And this is called a logistic regression, and a sparse one that would classify our set of features into benign and malignant. And how many features do we have here? If you are a bit picky, F1 to F, 855, right? And that, if you follow the golden rule that I said, what that means? It means that we had 10 times more of this data already, meaning that we had 8,550 images we didn't have. I'm sorry. So did we do anything wrong? If we were not careful about selection of our model and simply would choose logistic regression, then there would be a high likelihood of overfitting. But we went and we said that we want to have sparse logistic regression. And that sparsity is a key word, meaning that most of the parameters have to be 0. We have to kill them, like force them be 0, because we know that we don't have data, we want to get rid of you. So we give little chance of survival for the free parameters to become non-zero if they have to. Otherwise, they have to be 0. Sparsity means 0. Anyway, a little bit advanced here. But we will see. I mean, this is called regularization, by the way, in second lecture. So regularization is the way around circumventing having less data and like making the risk of overfitting less and less. Okay, congratulations if you are up until now following me. I know that you're tired. What about me not talking for about 5 minutes? 5 minutes, absolute silence. Here you go. Have a little bit of rest. Are you okay?
Can I ask you a question about the lab lessons, laboratory lessons?
Yes.
I don't know if you told something about them.
Yeah. No, no. There will be assignments, certain assignments that you have to take, and then there will be lab demonstrators and PAs who would help you to get around. So it's not like a free study, it's like a last 30 minutes.
And like the marks we're gonna, the points we're gonna get from lab lessons, they will like directly affect the mark.
Yeah, but it's not like explicit marks for your attending lab. Lab help interest in your like performance, because if you attend the lab, then you would understand and learn better. Similarly, you can then deploy that knowledge on your courses. So labs are helping your. Yes. Oh yeah, of course. We did it. We did it. Yes. You have a lot of freedom, and this is like a number of features that you want to replace, right? So, and my student decided that 855 is performing not too bad. He's looking at like the classification performance, but she could have done maybe less, maybe more, but it would maybe hurt or improve the performance of the classification. For example, look at the better picture, flower picture that we get later, better and before. Yes, but if you remember from Fourier this picture, I'm talking about Fourier transform. Since you have like this signature is precisely, let's say, um, 250 by numbers, and you've already got 155 descriptors. Yeah. So yes. Okay. Hmm. Yeah. Good. Absolutely. Uh-huh. Yeah. Yes. Entire included. Hmm? I think so. I think. I mean, my intention of disclosing this example is to teach you the process of machine learning. But this goes back to 2019. And since then, we have deep learning, and we have transformer models, we have a lot more advanced classification models that, do the hard job for us. As I said, they don't have to teach engineer how to calculate. So, but we have to know what's happening if we first by ourselves. That you have to decide, I have to decide which features I go from scratch by just having some inside opinion. So it's not always reassuring at 100%.
office S305. Yeah, it's S305. Yeah, S is important because we have SS in there. Yeah, yes. Yeah, yeah. It's irrelevant. You can choose really large models, really. But then you have, you, I mean, not always, but if you are a polynomial, like directly predicting x from y or y from x, yes. But you don't have it anymore, or you have barely such models in practice. So you have neural networks, and you have, like, these neural networks are like a composition of several layers that each of them is like each layer you can think of like a polynomial by itself. So polynomial gets in and makes analysis. Second polynomial takes it. Yeah, yeah. But you're not going to cover this learning in this course. I'm sorry, so but because it's totally different. So you're covering the basics, making sure that you're getting the foundation of machine learning right there, and then you have to keep learning the other things. Yeah, yeah, yeah. No, of course. Okay.
Okay, I reckon that was a good 5 minutes, right? Okay. So let's go back to our lecture. And as I said, we have unsupervised learning as well. And but unsupervised learning, a prominent form of it is clustering. So I almost, like 99% of the time, I think clustering is like a very prevalent form of unsupervised learning that you would perhaps face in the future. You may face it. Okay, so, here you see an example of that. So, so the general idea of clustering is to define groups of similar data points. Okay, so as you could see, in this case, we have a bunch of data points. Each green point here is a data point. And y-axis, x-axis determine two features. And what are those two features? One is eruption duration, and a second one is waiting time. And this data particularly comes from Old Faithful data set. It's a very well-known data set. It measures how geysers erupt. So the geysers are like fountains and sudden eruptions of water in some areas. So these are the measurements and observations. So each observation is a data point, and for each data point you have eruption duration, maybe here, and waiting time here. Waiting time means when the eruption has gone, how long we should wait to see the next eruption. Okay? So, because the eruption goes, and then nothing happens, and the second one, okay? And then you can have something like this, or and then half an hour later, something like that, all right? So, and the demonstration of the data, like the pattern that you heard here, is exactly expressed here, okay? You see that it's interesting because clearly the data is bimodal, isn't it? I mean, we have a group of geysers that are relatively short and they come fast, right? One after each other, relatively fast. But the ones who come with longer duration also come with long waiting time, okay? So that's what we could see from the data. So one group of similar eruptions here, another group of similar eruptions here. But wait a minute, didn't you just classify the data points in your mind automatically? You did, right? Just by looking at this data, you said and you agreed that the data is bimodal, and I agree, and it is bimodal. So in other words, you went ahead and you colored these green data points. You labeled them. So you went from all green to some blue, some red. You clustered them. Red cluster, blue cluster. So the way that you did this, you looked at the proximity of the data points and then how each data point is placed in the feature plane and how far close it is placed with respect to others or clusters that it might join. So again, we have the famous table that we have I mentioned earlier here. So you have features, but the third column here is missing, and you inferred that just by looking at data. And you're a human being, you did it, but we have clustering algorithms that allow computers to do it for us. And like what's happening here is a demonstration of how that algorithm works. And it's called k-means algorithm. And k here is the number of the clusters. For example, here 2-means algorithm. K-means algorithm means k clusters. So you wanted to cluster the data here into 2 classes or 2 clusters. By the way, how many clusters? How many clusters you go, given an arbitrary set of data points, how many clusters would you choose? Sorry? Yeah, I think so. Yeah, I think the best answer is to visualize them, right? Visualize the data and see, where the data live, and then take it from there. But as I said, after dimension 3, we can't do that. So the number of the clusters, again, falls under the problem of model selection, because you're selecting your model, and that's a hyperparameter. But let's go back to the k-means algorithm and have a sense of how it works. So k-means algorithm that will be, by the way, will be discussed in detail by Dr. Deligiani towards the end of the course. But it starts with random centroids or centers of each cluster. So you would say, okay, let's imagine that the red cluster centroid or center lives here, and the blue center lives there. And I would say the points that are closer to my red center, I would say, let's imagine that they are red points, and the other way around. So in that case, you have, I don't know how to say, I can't remember the mathematical name of this particular line. This exactly splits the distance between this red and blue centroids. So these guys go to the red cluster, these guys go to the blue cluster for now. Okay? Once you have got the points roughly in each cluster, you go and update your centers of the clusters. Okay? So because you have the data points in each cluster, you can compute the barycenter of each cluster, like just by taking the average of the features for each cluster, the clusters that you have temporarily made. And that would update your centers of the clusters. Look at the updated locations, one here, one there. Now, once you've got updated locations, then you go around back to the beginning and you update your, like, the decision boundary. Like, this guy has a lot better situation. And already by iteration number 2, you have almost got your centers or clusters right. You can go ahead and refine the clusters until a convergence happens. So you start with random centers, you update your memberships of each cluster, then you update your centers, and then you iterate until you arrive at convergence. And that's really, really simple k-means. Okay, so I think this could be an eye-opening clustering algorithm. Another clustering example happens when you wanted to color quantify an image. Here, our data to be clustered is the intensity not the intensity, because RGB level of each pixel in an image. For each pixel, you have RGB channels, right? So 3 features for each pixel. So if you have got an image of, say, 200 pixels by 100 pixel, and then you have got 20,000 data points, each having 3 features. And then you apply the k-means algorithm with k equal to 2, 3, and 10, and et cetera, to cluster the pixels, like the way that you did for the geyser data set. Nothing will change except for the dimension and the number of clusters. And as you could see, if you increase the number of the clusters, you get like more sort of realistic looking colors for the image. Like, for instance, with only 2 clusters, your image is barely an image. But you increase the number of the clusters, you get this lovely boy coming up from the picture. And same applies here. Okay. Closely related to clustering, I would disagree that the projection is like unsupervised learning, but closely related to clustering or unsupervised learning is projection, okay? And this is kind of important, but it's not learning. Projection is not learning. Is about dimensionality reduction. Because as I said, I mean, dimensionality, extra redundant number of features is your enemy in machine learning. You want to get rid of irrelevant information. Therefore, you have to deal with large dimensions. You have to reduce them. We have different tools like principal component analysis, TSNE, graphs, etc. You have different methods of projection. Projection of what? Projection of higher dimensions to lower dimensions. One strategy is like for instance, let me illustrate this example. What you're looking at here is So basically, you're looking at 100 genes here, or transcriptome data, in 100 different genes along the y-axis, and you've got 10 entry points for expression levels of the genes. So you have, for each gene, you've got 10 different measurements, okay? So your data now, or your features, reside in the space of 10 dimensionality. So in order to cluster them and maybe get an idea of whether you're doing the clustering right, you'd better go to dimension 2, because then you can see what's happening, okay? So then you are projecting the dimension of 10 to dimension 2. So which means that each of these black points here, each is one gene, okay? And as you could see here, our projection, whatever projection is applied here, I'm not sure. But the projection is kind of successful, because you could see if the purpose is the clustering, because we wanted to get a biological meaning out of, or a biological, like a knowledge or insight out of the data, the clustering makes sense left and right bunch. Yeah? Okay, so the projection, as I said, I don't introduce a particular technique here. I think will be one of your courseworks to double check. I'm sorry if I'm doubting so many things. The first time that I'm taking over this course for some sections. So that's the reason. Okay, that's called projection. Another nice example of projection is this paper that I was looking at, and I was amazed by the outcome. So this is a paper that says genes mirrored geography within Europe. And so what they have done is, like, they have, I think, 1,344 centers across Europe to DNA sequence people. Okay, some across France, UK, you name it, Spain, Turkey, etc., etc. Okay, different countries in Europe. So you know what the DNA roughly is, right? It's a big, really long sequence of letters, A, G, C, T, like this, right? So you've got that long chain of the letters for each individual. It's such a long that each DNA could be stored in 1 gigabyte of memory. So it's really huge. The dimensionality of the genes is huge. I'm not sure how many genes, by the way, each human being has. Do you know? Anyone? Oh, I'm lucky. Okay, so so they have applied PCA, principal component analysis. So from that huge dimension, they have gone to dimension 2. PCA dimension 1, PCA dimension 2. So they have mapped from somewhere imaginary in dimension of 1 billion something, they have mapped each DNA to a particular point here. So each point here is an individual, okay, here. So the strange thing is that, like you could see, they've got a genetic map in such a way that people from like the same countries have got their genetic maps very close to each other, very close, which means that people living in the proximity of each other probably have very similar genes in such a way that you can predict the location of the person or the area that the person comes from the gene by the accuracy of 400 kilometers. So, and I think it's really precious, for example, in investigations that might be issued by police, right? They look at the DNA of someone and they guess which area they come from. So, so this is not This is not clustering, this is not classification or regression. This is called projection. And so sometimes you project the data to get insights like this example. Okay, what about course structure? So the topics that we are going to cover is mentioned here, sorry. The first one is what is learning from data. We somehow covered that. We are going to have a detailed lectures, each on classification, clustering, regression, and projection, through which we're going to see how training, validation, and testing works, and how we are going to assess the performance, the metrics of the baselines of the models, and the common pitfalls like underfitting, overfitting that you almost know instantly in this class, and how we can present the results. So another point about the course structure, as I said, you're going to have probably most likely 3 units of case studies. You have to choose 2 out of them. 2 already has been secured. Third, I'm struggling to find someone. If I find, then you have to choose 2 out of 3, and then you're going to write a report, and you're going to submit your piece of code, and it's going to be assessed by us, and these are called case study. So each coursework is a case study, which means that it's a data set, and it's an exploratory problem to be solved and to be learned from. For each case of study, you're going to have a guest lecturer who's going to give you a 1-hour lecture, and practical sessions in the lab, and practical session by yourself at home, and a wrap-up session, a wrap-up lecture that would prepare you to submit your own work. And for this, I think we're going to make groups. So we're going to have groups of students, 5 or 6 of you in each group, and we are going to mark each group. It's not an individual project. So the assessment is exam-based, of course. Exam, 60% is exam, 40% is on top of coursework, 2 pieces, 40%, 20% each. We're going to have written feedback for the coursework. You have one-to-one help from GTA's demonstrators in the lab. I myself, I would come to labs. And lectures where solutions, so of course, the lectures we're going to discuss the solutions and common issues that you might have. It's not just about the theory, you're going to see a lot of coding points using scikit-learn as well. So at the end of the day, guys, don't panic and as it says, have fun, because if you go like emergency mode or panic mode, you won't learn. So it's opportunity for you to pick up and learn, okay? Let me know if you have any question, anything. My email is mentioned in the beginning, and my office is open for you, right? Any question? No? Have a good, oh, yeah. Yeah, you have a lab, but yes, you have, and would recommend that you join the lab, yes. Yeah. Anything else? Sorry?
For the attendance, did we take it for this lesson?
Attendance.
Usually it's like
Yeah, I think so, yes. I'll arrange it for next time, but today is already late, so. All right, have a good day, guys. Bye. No
for
worries.
the lecture.
No worries.
I love that you go into details. I really love that.
Thank you
I
very much.
appreciate it. For the groups, is there going to be like a forum place? Like in some of my other courses, the digital signal processing,
Yeah.
they have a specific forum place for us to like ask for groups. Is there going to be one in this?
Yeah, I think that we have a team channel that.
Team channel,
Yeah,
this one?
yeah, yeah,
Alright,
yeah.
I
I guess
didn't
so.
see it.
Yes.
I missed that, I
Yes.
guess. Yeah.
I mean, it's a bit, flagged in catching up, the logistics of this course because, as I said, this is my first time really. So
You're doing great.
thank you very much. So let's see. Yeah.
Yeah,
Thank you.
so
Yes.
much.
Yeah. Of course, yeah. Yeah.
So
Sure.
nice to meet you.
I want
You.
to
Yeah.
know more information about the group work, like so when will the group list be announced or something? Let me give you for you as we go ahead. I don't have answers. Oh, okay. So right now, it will probably probably we can say it on the Doodle afterwards. Maybe? Yeah. Oh, okay, okay. So it probably we, if not to, uh, make up our own group. We don't need to. I don't think it's not practical. Doesn't seem practical. You go and. Yeah, yeah, yeah. So that's no. You whatever you. Yeah, yeah, yeah. That's not very good. Yeah. Okay. That's all for now. Thank you. Good. Thank you. Yeah, yeah. Some automatic assignment. No, exactly. Okay. Yeah, because it takes such a long time, and it's scary. Thing is, it's become industry standard now, so I'm kind of right. We did have it didn't work out for a basic course like this. Students don't have that. We have the diversity of students in the level of student background. This is impractical for us to expose all of the students to. Is there any I guess so. I mean, there must be lectures that focus on emotional learning. Take artificial intelligence with Edmond Paul, which brilliant. I think kind of covered. Yeah. Thank you. Hello. I want to know that is yeah, the case studies will be determined by the guest lecturers, and there are certain paths that you have to go to. So it's not like predetermined. Like yes, yes, yeah, yes, yes. Because otherwise our assessment can be incoherent. I think each group will be assessed for the case study. Yes, yes, yes. So every 5, 6 of you will make a group, and the group will be responsible to deliver the code, reports. No, I think there must be some automatic assignment tool. It's practical to have like this many number of students decide who goes with whom. No, I'll do it, or I think so. I mean, as I said, it's my first time. I have to go investigate what's happening in that area. Okay, that's a bit gray area, but I'll let you absolutely know what's going to happen next. Okay, don't worry. I tried to record it. Yeah, yeah. Yeah, well, it's automatically must be available to you by a model. I think so. I think so. And I don't know which, you know, um, links or websites that you could go to. I asked the guy to activate it right before my lecture. So there was a guy here I asked him to just record the lecture. And he said it's okay. Yes, it's okay. So I assume it's okay. If it is not, I'll sort it out next time. Okay? Yes. No, I'm ethnically Persian, Iranian.
Sorry?
Iranian. Iranian.
Iranian, yeah.
Yes.
So Arab because my professor at the university is Arab too. He's Iranian.
Who?
That's Saad. You know? He's teaching in Italy right now. He's from Gaza originally.
Oh, right. Okay.
He's a professor from Gaza.
Oh, okay. No, I don't know him.
You already know him. Oh,
No,
he knows you. I don't know. Nice to meet you.
Nice to meet you. Yeah, have a good day. Yeah, good. Medical immunologist. Yes. Oh, that's pretty trendy. Yes, yeah. Where's the Actually, um, yeah, a local PhD student for clinical. I don't have time in the study of but and there are scholarships you can apply. Of course, there are pathways that you consider applying for the scholarship for PhD. If you want to do it on medical imaging, yeah. Okay, yeah, good. Hello.
I'm one of your students.
Okay.
Very quickly. I'm with one of the societies on campus called Climate Change.
Right.
We do like treks and marathons for everyone for charity. Do you mind if I take like a minute to talk to them before we get going? Or?
Did you say a minute?
Literally just like a minute.
Yeah, go ahead.